Schrödinger's equation is going to allow us to solve many important problems in quantum mechanics. Before doing that, we should think some more about how wave functions and particles all work. A classic thought experiment that exposes some of the subtleties of quantum mechanics is called the two-slit diffraction experiment. Now, this is based on a well-known and quite remarkable experiment in optics. Indeed, a key experiment that actually clarified the wave behavior of light. The experiment in optics is known as Young's slits, after Thomas Young, who performed it in the very early 1800s. So we will start here by looking at Young's slits as just a classical experiment with waves, before we go on to look at surprising consequences for the way we're going to look at quantum mechanics.
The idea with Young's slits is that we have some mask, and we've cut some slits in this mask, and these slits are a distance s apart. And then what we do is we shine a wave, which you can think of as a plane wave, onto this mask from the left-hand side here. So we've got light coming into these slits. The question really is, what's coming out the other side of these slits? And in particular, if we go to a screen at a very large distance here, so some very large distance z0, what are we going to see on the surface of this screen? So we need to figure that out. So what we do is we use our Huygens-like construction, and we consider each of these slits as point sources, giving us circularly expanding waves. And the result of that will be some interference pattern over on the screen, which I've shown by this bar here, showing dark and bright and dark and bright and dark and bright regions, corresponding to the bright, dark regions of this interference pattern that we get. So, as I said, just two circularly expanding waves here coming out of point sources that we regard as having been generated as effective sources by this plane wave that shone on the left-hand side of the slits. Now, let's look at the details of this a little bit, because we're going to be able to figure something quite explicit out here. We look at some distances. So these slits were a distance s apart. So from some center line here, we've got a distance s over 2 to this slit. We have our distance z0, of course, we said was the distance between the mask here and the screen. And specifically, let's look at some point x on this screen, this point x up here. And note that this distance from the slit up to the point x will be x minus s over 2. So this x minus that will be this height here. Now, we can use Pythagoras' theorem to calculate the distance from this upper source here, this upper slit, to the point x. It's simply, we take the square of this distance, we take the square of this, we add them together, and we take the square root. And that gives us the length of this line here, that distance. So we can do some algebra on that. We can take this expression inside the square root here, we can flip it round. We can take out the z0 squared from inside the square root and take it out as a z0 outside the square root. So this used to be z0 squared here, for this z0 squared, but we've taken that z0 squared out, which becomes a z0 outside the square root. And similarly with this term here, we have to divide that by z0 squared. So now we've got something that is z0 times a square root of 1 plus something or other. And we're going to be presuming that this distance x, indeed x minus s over 2, is small compared to this distance here. That's an assumption of our model. We're saying this screen is a very long way away. Well, because of that, we can do a power series expansion of the square root. And 1 plus a small quantity with the square root taken of that is approximately 1 plus half of that small quantity. So the square root of 1 plus delta, if you like, is approximately 1 plus delta over 2. So doing that, using this power series expansion of the square root, because this thing here is a small number, we get what we have down here. It was 1 plus half of this, all multiplied by z0, so that's z0, plus this over 2z0 instead of z0 squared here. And we can multiply this out here, and what we get is a set of terms. These ones here, we're going to group them later on. The important term we care about is this one here, minus sx over 2z0. Similarly, we can look at the distance from the lower slit to this same point, x. And obviously this vertical height here is now x plus s over 2. The horizontal distance is still z0. So the distance from the lower source to the point x on the screen is the square root of this distance squared plus this distance squared. That's our square root here. And we can do a little algebra on that. The same kind of algebra as we did before, doing our power series expansion of this square root and rearranging terms. We get the same as we got before. With all this stuff is the same as we got before for the upper slit. But now we have plus sx over 2z0. For the upper slit, we had a minus sign there. Okay, so let's look at the waves that we're going to get on this simple calculation. We will presume for simplicity that at the screen, the waves from the different sources are approximately equally bright. The screen is a very long distance away compared to the separation of the sources, so we just presume that the waves from both of those are going to be equally bright. And so, using exponential waves for convenience here, they're easier to work with, our wave on the screen is going to be proportional to the sum of two waves, one from the upper slit and one from the lower slit. And you see here the distances that we had on our diagram. So we can use our approximate formulas for the distances that we worked out before. And here is our plus sx over 2z0 that came from the lower slit, and here's our minus sx over 2z0 that came from the upper slit. And we have lumped all the rest of the terms in our distances into an exponential factor out the front here. And this alpha we have in here is k times all of the other terms that we had in both of our expressions for the distances. So we just separated that out as a factor out the front here. Now, we remember that e to the I theta plus e to the minus I theta is just 2 cos theta. So this expression that we had here from the previous slide, we can rewrite in the following form. And if we want, I can write that back in terms of lambdas here instead of k's, if you like. There's no difference. It's just the same expression, but with lambda instead of k. So the intensity of the beam, which even with classical waves, when we use exponential waves, we think of as the modulus squared of the wave itself, that's going to be proportional to cos squared of this over here. The e to the I alpha times e to the minus I alpha will just give us 1, so we can drop that anyway. So as I said, the intensity is proportional to cos squared, or if we like, we can write out cos squared in terms of a half of 1 plus cos of twice the angle of interest. So this is the interference pattern that we see on the screen, the brightness that we see on the screen. So we have our interference fringes here. They are spaced by some amount ds. And in our algebra that we just did, because of that cos term that we had in here, the separation of these interference fringes, we now have a formula for it. So we got that formula from our cosine expression, that the interference fringes are going to repeat with this distance here. So in the classic Young slits experiment in optics, this enables us to measure the wavelength. It's a very clever idea because we can measure these fringe separations here as quite macroscopic distances. This is a long way away from these slits. And in a real experiment, we would make this distance much larger and this screen would be much larger. So we can measure these distances, the interference fringe separations here, as quite macroscopic distances. And as long as we have a way of deducing just how far apart these slits are by looking carefully at them, we can measure quite small wavelengths, even with all of these distances being quite large. Now that's the real trick of Young's slits experiments in optics. It enables you to measure the optical wavelength without ever having anything whose size scale is the optical wavelength. And that would have been very difficult in the early 1800s. So it's a very cute experiment in optics. However, our interest in this is not so much the scale here, although we could certainly use this size scale to measure electron wavelengths if we're sending electron waves in here. Our interest in this is a bit more fundamental in terms of interpreting what's going on.